Hello, everyone. What we're going to do in this lecture, we'll talk about some basic organic chemistry concepts, which are behind, if you want, the structure of those biomolecules that we'll talk about in the next few lectures. By biomolecules, I mean like proteins, nucleic acid, carbohydrates, and lipids. So what we'll talk about here is, first of all, we'll define what organic compounds are when compared to inorganic compounds. Then we'll talk about why carbon is the main element that makes up the basic structure, basically, of all the big biomolecules. Why carbon and not another element? And you see that all these properties ultimately come from the number of bonds the carbon can form and also the angle of the bonds that it forms. And finally, we'll talk about the functional groups. By functional groups, we mean these clusters of elements that combine together can modify the carbon structure, which is the base of the biomolecules, giving the biomolecules specific properties in terms of polarity and function as well. Starting from the definition of what is organic. Well, this is still a fairly blurred distinction between the two type of compounds, if you want. In fact, even if you go to the UPAC, or the International Union of Pure and Applied Chemistry, this is basically the organization that is in charge to classify and name all the chemical compounds that are known. So even if you go to the website, you can't find a real clear definition of what is organic, what is not inorganic. So there used to be an old definition, which is where the name comes from too. Based on this historical old definition, organic molecules were molecules that were made by living organisms, whereas inorganic molecules were those that were found only in non-living organisms. So it was based on the assumption that there was a clear, uncrossable separation between living and non-living organisms. However, in the first half of 1800s, this scientist Waller, for the first time, he could synthesize an organic compound, urea, from an inorganic compound such as ammonium cyanide. So showing that in reality, there may be a connection between these different type of compounds. So there cannot be this definition just based on the assumption of different compounds, completely separate compounds. So a more reasonable definition nowadays is that organic compounds are all those compounds that do contain carbon and eventually oxygen as well, except for small molecules such as carbon dioxide and carbonate and so on, very tiny molecules. Whereas inorganic molecules are compounds that are found only in non-living organisms. So here you have some example on the bottom. So on the left, you can see some compounds that are defined as organic. You can see these will be a glucose, the structure of beta glucose on, sorry, I'm gonna put the laser pointer. This is beta glucose. This is the structure of one nucleotide. This is the structure of a fatty acid. So all of them are rich in carbons. Here, where you don't see what is specified in these corners of this molecule, it is implied that there is carbon. So there's carbon here, carbon here, carbon here. So all of these are classified as organic compound. Now, these compounds here instead are classified as inorganic, and the reason being that they're found in non-living organisms such as carbon dioxide and so on. There is found in living organisms as well, but it's a small molecule. Even though it contains carbon and oxygen, it is considered a small molecule, and therefore it's classified as inorganic. Now, why carbon? Why is carbon this main element, or if you want, the most important basic element in all biomolecules? If you remember, if you go back to the lecture when we were talking about the basic chemistry, and you were looking at the composition of or the abundance of carbon on Earth, and you would see that carbon is actually not one of the most abundant compounds. However, it's extremely abundant in organic molecules. Why is that? Well, The reason why it's so abundant is because of its versatility. Because ultimately, the presence of 4 valence electrons in carbon allows them to form 4 covalent bonds. Not only that, but also the angle of these bonds, as you can see in this picture, 110 degrees, allows for carbon to actually form very different structures. So it can guarantee both variability and in terms of what can be attached to it by having a lot of bonds possible, and also in terms of three-dimensional structure. So the 4 bonds, in the end, what they do, they allow for different things. They allow for the formation of very long molecules, great property, which is not a compromise between length and variability. What I mean by that is that if you look at this string of carbons here, so these would correspond to a long molecule, even though carbons are attached to each other, they still have additional bonds that they can form by substituting these, for example, hydrogens, with other molecules. So carbon allows, because of the 4 possible bonds, the formation of long molecules that can still be modified in so many different ways by adding different groups, such as this methyl group here. Here you could have what is an hydroxyl group. We'll define these groups later on. So can form long molecules and which with a lot of variability. Imagine if instead of carbon, nitrogen, for example, was the element found in organic compounds. Now nitrogen can form 3 bonds. So in stretches like this, you would have only one additional bond available here. So the variability in long molecules given by an element like nitrogen compared to them will be much lower. Not only that, but now carbon allows us to form these long stretches and strong molecules too, because it allows to form still also double bonds, but still the possibility of creating different variables. Imagine this molecule here. Now there is a double bond between these 2 carbons. So these 2 carbons cannot rotate compared to each other, whereas they could do in this bond right here. They can't rotate anymore, so there is strength here in this molecule. Despite that, you still have 4 possible other bonds here, where carbon, or this molecule, could be modified. So you can see how many variables you will get. Imagine these being nitrogens with 2 bonds with each other. You would have only one here and one here, much less variability. Now, this is done not only with double bonds, but even with triple bonds, even stronger molecules. Even in this scenario here, you can still have some variability left, something that with nitrogen, for example, you could not get, because if nitrogen would be joined with 3 bonds, you would have nothing, no more bonds possible left for the 2 nitrogen molecules. So carbon, because of the 4 covalent bonds that it can form very strong, very long molecules that can be also very strong because it can introduce also double and triple bonds. And these long molecules can also give a lot of variability by adding different other components to the remaining bonds left for each carbon present in the long string. Together with that, because of the angle, which is about 110 degrees, now carbon can also form or give variability also in terms of 3-dimensional shape of the molecule. So it forms not only long molecules, but also circular molecules, which can be extremely helpful for different reasons. They're very helpful, for example, for absorption of photons and other creating other strong or structural molecule or hormones like this one right here, typical steroid, which is formed by all these carbon rings fused together. Now, the 4 major classes of organic molecules that we'll talk about in the future lecture, in the next lectures, are going to be carbohydrates, lipids, proteins, and nucleic acid, which include RNA and DNA, so ribonucleic acid and deoxyribonucleic acid. Now, all of these molecules in general are formed through the polymerization of different monomers, different subunits, which is done through 2 types of reactions. So the formation or I should say done and undone through two types of reaction. The formation of this molecule is done through dehydration synthesis. This is called dehydration because the joining of two molecules or two groups in the monomers leads to the formation of a water molecule. Instead, they are degraded, and you see, for example, when we talk about glycogen, amylopectin, amylose, and so on, they get degraded through reactions called hydrolysis, which basically are the opposite of dehydration. So the two groups that were joined before are now separated through the introduction of a water molecule, which is split among the two groups. Now, we'll see later on. We'll talk about the properties of the different biomolecules. We'll say, oh, this molecule is extremely polar. The phospholipids have non-polar tails. They cannot interact with each other or with polar molecules, and therefore they do interact with each other, forming phospholipid bilayers and so on. Well, where are all these properties coming from? All these properties come from these groups that are attached to these biomolecules, which are called functional groups. The name itself implies not only that it gives it the property of polarity, non-polarity, being hydrophilic, hydrophobic, but also they determine the function of molecules. I have an example at the end of the lecture when I show you two steroids compared to each other. You can see how just changing some functional groups or the location of the functional groups, you actually change the function of the molecule itself. So what are functional groups? Functional groups are a cluster of atoms which are attached to a carbon of another molecule. For example, this is an hydroxyl group. We'll talk about in the next slide what it is exactly, and the property of this hydroxyl group, which is attached to the carbon right here. So this is a functional group per se. Now, as we said before, they determine the property of the molecules, and here you can see exactly the effect of the functional group on this molecule. So this is ethane. Okay, ethane. So ethane. So this molecule per se, it's a hydrocarbon, has no polar bonds, is a non-polar molecule, and therefore it tends to be hydrophobic. So it will not dissolve well in an aqueous environment, so in water. Now, just by adding this functional group here, this hydroxyl group, the property of this molecule changes dramatically to the point that now you're adding a polar group here, which actually will make the whole molecule here polar and therefore able to dissolve in an aqueous solution, so hydrophilic. So you can see the impact that a functional group such as the hydroxyl group here can have on this molecule. And this applies to many other functional groups, which we'll discuss from now on. So the first group that you find extremely abundant in biomolecules is the hydroxyl group, which consists of an oxygen with a single covalent bond to a hydrogen, and this group is attached to a carbon in another molecule. So this is the hydroxyl group as a functional group. Now, if you recall, this bond between oxygen and hydrogen, it's a polar, and therefore this group will add polarity to any molecule that is attached. And we saw an example in the previous slide. Now, this effect obviously is different depending on how big is the molecule it gets attached to. So if you are talking about, for example, a small hydrocarbon like this one, yes, it has a clear effect. This becomes a big percentage of the new molecule. But now if you're talking a very, very long hydrocarbon molecule here, obviously the impact will be smaller. Now, it's commonly found in the active site of enzymes where it participates to the binding of substrates, and obviously it's the base of several alcohols like commercial alcohol and wine and so on. The second group we're talking about here is a methyl group. Now, a methyl group consists of a carbon and 3 hydrogen attached to it, and these will be attached to another carbon site. For example, this hydrocarbon here or another molecule there. Now, These bonds are non-polar, and therefore this functional group will make anything that gets attached to less polar than it was before, so more hydrophobic. This is a group that is commonly used also in nucleic acid, for example. Some nitrogenous bases, we'll talk about the structure of nucleic acid in one of the next lectures. By being added to some nitrogenous bases, actually this protects some of the nucleotides from restriction enzymes. It can also inactivate the expression of the genes that do contain these nucleotides and so on. A third group, or it will be actually a double group per se, of functional groups that you find, particularly in carbohydrates, such as glucose, fructose, galactose. You'll see them later on when we talk about carbohydrates, are carbonyl groups. Carbonyl groups, they have a shared feature, which is the presence of a carbon with a double bond to an oxygen. Okay, this is, as soon as you see a group that has this and doesn't have an hydroxyl group attached to that. So if this is attached to a hydrogen and a carbon, or a carbon and a carbon, you immediately will say that's a carbonyl group. Now, these can be of two types, depending on the location of this carbon-oxygen bond there. So if it's located at the end of a chain, such as, for example, look at glucose here, this double bond correspond to the last carbon in this chain. So it's a terminal carbon. In this case, this carbonyl group is referred to as an aldehyde. Formaldehyde is an example. Obviously, it's a single carbon, so it has to be the terminal carbon as well. But you can find it here in glucose. You can find the same thing in galactose, for example. It is on the terminal carbon, so it's an aldehyde. Whereas if this carbon with a double bond to oxygen is found within a chain, such, for example, here in fructose, you can see this is not a terminal carbon. It's attached to a carbon one side, and another carbon on the other side. So in this case, you will refer to this carbonyl group as a ketone. Okay. Now, these are very reactive groups. In fact, you see that these are the groups, together with the hydroxyl group here, which are responsible for the formation of the cyclic form of glucose and fructose and other monosaccharides with 5 carbons or more. We'll talk about that when we talk about carbohydrates. So also this bond between carbon and oxygen, it's a polar bond. You can double check with the electronegativity values if you want. And therefore, they will bring polarity to any molecule that they get inserted into. Another important group, and I put it right after the carbonyl group because I want you to learn that this is a different group, okay, is the carboxyl group, okay? So don't confuse it, please, with the carbonyl group. The carboxyl group consists of the combination of a carbon with 2 bonds to an oxygen and what we called before an hydroxyl group. Please do not call this a carbonyl group and this an hydroxyl group. When you see them combining together, the only thing this is a carboxyl group. Also because these have different properties when they're combined together compared to when they are separate to each other. So the functionality brought by this group is different than the functionality that is brought in by only a hydroxyl group separately. So this is a carboxyl group, 2 bonds to the oxygen and a bond to an oxygen here and a hydrogen here. So now, these are found usually on a terminal carbon. You'll see it on, for example, fatty acid at the end of fatty acid chains, and are commonly found in all amino acids. So all amino acids, they have a carboxyl group, which is referred to as the alpha carboxyl group. We'll talk about that. Now, this group has 2 big properties. It's very polar, as you can see it. This is a polar bond. This is a polar bond here. So it's a very polar group, so it brings polarity to any molecule it gets attached to. Not only that, but if you remember, when we're talking about acid and bases, I use as an example acetic acid as an acid, and which is basically this group with a methyl group attached to it. And so this group is also an acidic group. These hydrogen here tend to be released, losing the electrons, which stay with the oxygen here. So it tends to dissociate and therefore release protons in the solution. As any molecule that releases protons in a solution, so this is defined as an acidic group. So any compound or any molecule that would include this group would have additional polarity and would be an acid. Amino acid, that's where the name comes from as well. So it reminds you that part. Now, the other group commonly found in amino acids is the amino group. The amino group consists of a nitrogen, right here, attached to two, and I stress two hydrogens. So there is a nitrogen attached with two covalent bonds to two hydrogens. Now, sometimes you see with three hydrogen. In reality, the third hydrogen is not covalently bonded. In some picture, it's shown as a covalent bond, but it's not. What happens is that this group acts like as a base, so it's an alkali group, and therefore can bind protons. And the way it binds it, it doesn't bind it through covalent bond, but through electrostatic interaction. So the positive charge of a proton is attracted by the partial negative charge of nitrogen here. And so it's an electrostatic interaction, it's not a covalent bond, okay? So it's never really part of the amino group. The real amino group is NH2. If you see NH3 plus, it means it has bound a proton through the electrostatic interaction. As the carboxyl group, also this is made with polar bonds, and therefore it's a polar group, which would increase the polarity of any molecule that is attached to, such as this amino acid, which you can see has a polar group and acidic group here, and this amino polar and basic group right here. Another very important group in biomolecules is the phosphate group. The phosphate group is a very, very strong polar group, acidic as well. I forgot to put it in this slide, but it's an acidic group. These protons here get released very easily, and therefore these work as an acid itself. So a molecule that contains a phosphate group will be a very polar and will be an acid, okay? Would have an acid component. This is found in nucleic acid and nucleotides, the components that make up nucleic acid. Extremely abundant there. Here you see an example of a nucleotide. This will be a ribonucleotide, one of the nucleotides that make up RNA. And each nucleotide, triphosphate, will contain 3 phosphate group here, and which then are found, one of them, this one being here, this one right here, would then be found also in the strands of DNA, like in this case, or RNA. So as a key component, what we call the backbone. We'll talk about that. Now, the phosphate groups are also used to store energy joined together in nucleotides, particularly in ATP and GTP as well. These phosphate group joined here, they store a lot of energy in these bond here. So, and this energy is released by hydrolyzing them. So by adding a water molecule here through a hydrolytic reaction, which we talked about earlier on, a phosphate group can be released together with the energy associated with that. So these groups, or phosphate, are important for not only add the polarity and making molecule acidic, but also for energy storage in some nucleotides. So finally, last group we'll talk about is the sulfhydryl group. This is a group consisting of a sulfur attached to a hydrogen here. Now, in terms of polarity, is borderline this. If you calculate the difference here, it will be below 0.5, but some people consider it as polar. So I would consider it still as a polar group overall. And this is always found at a terminal carbon, and it's a group that is found in several amino acids, like cysteine, for example, so components of proteins. And when they are found in amino acids, in polypeptides, these groups, two of them, they tend to react with each other. So you see this group here and this group here. They will react with each other, forming a direct bond, which is referred to as the bridge. Both bridges are extremely important to give permanent folding to proteins as part of what we call the tertiary and quaternary structures. I'll remind you that when we talk about proteins. So, putting all these functional groups, as I said before, determine the properties of the molecules in terms of polarity, whether they are hydrophobic or not, and so on. Not only that, but they determine also the function. And just to give you an example here on how these groups are important for the function, not only based on the type that you find in the molecule, but also on their location. Here you have a picture of two hormones or types here. So these are steroids, okay? They're actually considered lipids. And so they can exist in different forms. So this is one of the example of estrogens that you find. One of those hormones that will basically lead you to those characteristics of a female. Okay? Whereas this is testosterone. Of the same family, similar to estrogen, but instead, if you express high level of testosterone, you would develop a typical male traits, such as going to Home Depot all the time on the weekends. Now, if you look at the difference here between them, the difference is really, really minimal overall. Actually, in fact, they have the same functional groups. They have a ketone here, both of them. So this will be a carbon. This is a double bond to oxygen, and it's in between carbons, so it's a ketone. Then there is a methyl group here, one in estrogen and two of them in testosterone. So when you don't see it here, it means that there is a carbon, and since there is already a bond here, it means that the three other bonds will be with hydrogen, so a methyl group. And then there is an hydroxy group located in different parts of the molecule when you compare estrogen to testosterone. Now you can see how just switching these groups causes a complete switch in function of these hormones, and therefore a complete change in where they are expressed in the organism they are expressed. Hence the reason why these groups are called functional groups. So in summary, in this lecture, what we talked about, we defined the difference between inorganic and organic compounds, even though the definition is still fairly blurred. Then we talked why carbon is so important in biological molecules, and ultimately this is all due to the fact that because it can form four bonds, it can guarantee variability and strength at the same time. Variability both in terms of long chains or three-dimensional shapes. And finally, we went through the different types of functional groups, and we discussed also their properties.